So welcome to our specialty webinar here in December. Obviously very appropriate, the cold weather training webinar. Thank you guys for coming. Hope everyone's doing good today. So it's going to be interactive. So you guys can drop in the chat at any time, which is that bubble in um, the bottom of your screen where the video is. And then, feel free to stop and ask questions at any point. But we're gonna get rolling into it. So we got a lot of good, cool, interesting things to be going over. And the first thing I'm going to do is share my screen so you guys can see what I'm looking at. And I just have to figure out how to do it. Oh, it's that big one right in the middle. Found it. Okay. So let me know if you guys can see my screen. Yeah? No?
Yeah, I got it.
Okay, awesome. So, cold weather training. Here we are today. So, um, obviously going to be an interactive webinar, trying to go over a lot of different aspects of what happens when we're in the cold. Certain facts about the cold weather and cold environments that a lot of people probably don't even maybe fully understand. Some of like the obvious concerns and the risks and a little bit of those details, but then also, what we can do when we're trying to exercise and do our actual training. And then of course, all those different things. But then I'm also going to go over at the end a couple of cool features of like different examples of where we've really been able to do some impressive things in cold weather. We as in human beings, I haven't done anything that impressive. I've just kind of gone running and stuff. But anyway, so I wanted to open it up for questions before and after. So, and of course, welcome any questions during. But is there any questions that anybody had or curiosities or anything like that when it has to do with cold weather, training, what to do, what not to do, anything like that? Don't all jump at once.
Uh, no, I've never done it a lot, so any information would be new, I think, to me.
Awesome, cool, yeah, absolutely. So we're gonna give you just about all the information you'll need, and then maybe even a little bit more just for fun. Yeah, so if you, at any point have any questions about anything, just feel free to stop me and give me a shout. Same for anybody else. So what we're gonna go over today, why do we feel cold? Like that whole concept of like feeling cold and what that means and stuff like that. What our bodies and then ourselves do to stay warm. The second part of that's pretty obvious. We all know what to do. We don't go out in bathing suits in the middle of winter time, right? So we know what to do to stay warm. Our parents probably yelled it at us when we were little kids. What happens when our body cools down? So our core body temperature. This is that little bit of like danger zone I was talking about when things really start to kind of go bad. And then, of course, during exercise, tips, tricks, what you should do, what's going on with your body, things to be aware of. A little surprise portion of a few unique examples of things that we've been able to do as a species in the cold. And then also, of course, any questions at the end. And you can stop me at any point, too. So what is cold? So few different things. So the environment, I wanted to emphasize these points here. Obviously, temperature, that's the one that we all probably know of when it's, we see what's the temperature outside, how cold is it? Wind, so in our area in particular, where we have a lot of windmills, we know all about wind, but a lot of people don't fully understand wind and the effects that has. Water is an entirely different thing. So we know that we get like really cold when we go into water. Like if it's, I mean, we're on the West Coast here, the water temperature is between like 60 and 70 degrees. If you're outside in the air, 60 and 70 is not too bad. So the one thing I really want to mention with water, because it's important when you exercise, you can get wet from sweat and potentially other things depending on the exercise that you're doing, like snowboarding or something. But when your body is covered in water, just the way that the cooling works with like the physics and stuff, I don't want to get too scientific with it, but the way that whole thing works is basically 4 times faster. So that means that it takes a quarter of the temperature change to cause a lot of these health concerns when it comes to anything having to do with cold water. So there's a reason we can withstand, 107 degree water temperatures in like a hot tub, but we can't really go too far below our core body temperature. So below, I think it's like 89 degrees or 85, somewhere along like water temperature, 85 to 89 degrees. That's when you start to go at risk for hypothermia. if, for long periods of time, depending on what you're doing and stuff like that. For exercise, they say somewhere in like the high 70s, low 80s will work because we get a little bit warmer when we exercise. But yeah, so water is a little bit unique. We're not going to go into too much more detail on water, but it's definitely something to keep in mind if you're training or preparing for anything outside. Whether you're doing some yard work and you're like maybe washing the car or something like that, or like I said, anything where you're in the snow, anything on the ice, fishing, maybe something like that. Anything where there's water that could be involved, it is going to sap your energy and your heat 4 times as fast. So just keep that in mind. And then wind chill, I put that there as a question mark. So temperature is obvious. Wind, the reason why wind is even a factor is because there's 4 different ways that we can actually lose heat. And the most important one is convection, which is basically air coming in contact, or water coming in contact with our body and then pulling heat away from our skin. So wind chill, a lot of people don't fully understand it. It's an index. So you have like body mass index, which is a combination of height and weight, and you just get like a kind of like a combination number. We don't really use that anymore, but we still use wind chill, which is just a combination of temperature and wind. So a temperature of 30 degrees is really cold, but if there's no wind and it's sunny, it's not that bad if you have a couple layers on. Whereas a temperature of 50, 55 is not too bad, but if you have like 20-mile-an-hour winds, now it's going to feel like 20. So it's that combination of them. So wind chill, just know that it's basically the mix of the two. A lot of people don't really fully understand that concept. So, but then our bodies, so we touched upon this a little bit, and again, I'm not going to try to get too scientific with it, but long story short, in our skin, we have all over, we have receptors, which detect, there's receptors for a lot of things. In this case, it's the receptor that can detect changes in temperature. So we can feel like a dull push, that's one type of receptor. We can feel like a needle prick, that's a whole different type of feeling, right? So this one is a whole different type of feeling that's just for temperature. And our hair is another factor for that convection that I mentioned before. So that's what's going on our skin when it comes to cold. We get goosebumps, our hair stands up, that whole kind of thing. We're trying to stop that wind from moving. And then so the ways we lose heat, basically heat loss, like I said, there's a few different ones. Convection is the biggest one. The other one is evaporation, but normally we think of that when it's warm out because we sweat and we lose heat. So that's the evaporation there. We usually don't do that too much unless you're sweating in the wintertime, which is bad, and we're going to get into that because you don't want to try to exercise, warm your body up, and then have that cause your body to try to cool itself off. It's a really kind of bad situation. And then so tissues that help. We're going to do a little bit more on this in a little bit, but essentially there's 2 main things that help us when it comes to keeping us warm. And those are the fat around underneath our skin, around our whole body, and then also our muscle, so muscle mass. So I mentioned these because there's a couple of examples that will kind of put all this into perspective. So children, little kids, they have what's called a higher surface area to body mass ratio. Basically, as we become adults, our body mass changes, but our surface area doesn't change as much. So it basically will help us kind of insulate our core body temperatures. Children are usually very lean. They're usually a little bit like kind of relatively like longer for the body mass that they have. So children are a little bit more susceptible to cold weather conditions and the health issues from that. People who are very muscular or have a lot of fat, they're larger people basically, they are usually more resistant to cold temperatures because they have a lot more of one of those 2 tissues, sometimes both. And then elderly are also usually very susceptible because naturally when we get older, we lose muscle mass with age. So it's usually those 2 tissues or some combination thereof that has to do with why people feel so cold and why they don't, or why they're more resistant. So the overall goal is basically to prevent heat loss. And our body has a few different ways that it tries to do that, which we're going to get into. So this is a little illustration. I should have clicked on it a little bit earlier, but basically you have 2 different areas of fat and then muscle in between. The visceral fat is around the organs. That's a little too close inside the body for it to help us really fight off cold. It's only the outermost fat and then the muscle there. Those really help us a lot when it comes to being resistant to cold. So the body's reaction, what it tries to do, there's 3 main mechanisms, and they kind of go in this order for the most part. There's restriction of blood flow to the skin. So this makes sense when you think about it. In the summertime, skin usually gets a little bit redder in color. It's a little more like vibrant and stuff like that when we're sweating and stuff like that, or when we're stressed and we're really worked up. That's because we're rushing blood to the skin. And when you do that, you'll provide more liquid for your sweat glands, and then they'll be able to sweat more and evaporate. So that's in the summertime. So in the wintertime, we just simply do the opposite. So if you take away the blood flow to the skin, that blood won't cool off as much, and the blood circulating around inside your organs is going to stay a little bit warmer. Um, and then increasing metabolic rate internally. So shivering, we know what that is. You're constricting your muscles kind of on and off, like in a shaking fashion, to kind of generate heat from those skeletal muscles on the outside. That one we all pretty much understand. That's not the same as increasing your internal metabolic rate. So basically, what your brain will try to do is release stimulation to some of your other organs to basically help them increase their metabolic rate, so that your organs are kind of like working harder to do the same job, and that will help generate a lot of internal body heat. So those two go on when we don't even realize it yet. Shivering is really the only one we notice. So shivering is also the last one. So that means once you've gotten to that point, these other two have already been going on. People who are very resistant to the cold, they probably have these first two going on a lot more and just a little bit better. And that's why we don't see them shivering as much. Whereas other people who are not as resistant, either these mechanisms aren't working in full force, or they're just not having the same kind of effect. Could be a variety of reasons. So that's in the short-term sense, like right when we go outside. Adaptation, so long-term. So the jury's still out on this. They don't really have the concrete details figured out, but there's a lot of people who are trying to figure it out for a lot of different reasons. But what they do know is that with repeated exposure, so basically being outside a lot, like if you work outside, your body will kind of be a little bit more resistant. Same thing with long-term exposure. So like if you live in a really cold climate, your body will be a little more resistant. And what they think with these two is that when those are going on, of the three mechanisms, it's the first two that are happening. So that change in blood flow and then the increase in metabolic rate inside. But because you're not really shivering as much, they think that these people with these adaptations are able to function with slightly lower core body temperatures, which sounds a little bit weird because generally when our core temperature goes down, it causes a problem. Same thing if it goes too high. We don't function with 103 fever, right? Same thing, we're not going to function with like a core temperature of 93 degrees. So they're still not sure, but I think that might actually be something that goes on in certain people. And of course, exercise. So getting used to exercising, which is something we do consciously, of course, that can help increase the internal and external metabolic rate. And exercise will also change the blood flow to the skin automatically. So it kind of does all these already for you. And then tolerance. So tolerance is different than what your body is able to function with. Sometimes we shiver a little bit like ahead of time just because we think that we're cold, even though your body's actually fine. And sometimes vice versa. We may not feel like we're cold, but our body is actually like really suffering. And that's why I put like in question mark doesn't matter. We're still trying to research this. But if you've ever had a fever, you know that like your body's obviously running really hot. You have a high temperature, like 101, 102, maybe something like that. But you might feel super cold and be shivering. So that's why the tolerance thing is a real question mark. It's not really the best representation of what's going on inside. So I just wanted to mention that really briefly to keep that kind of part with a grain of salt, because it may not be exactly what your body's going through. So this is what your body tries to do to withstand the cold. So what happens in cold environments? So right away, we mentioned the receptors, the reaction, that's going to get sent up to your brain. There's a part of your brain that's responsible for this concept of homeostasis, which is just simply maintaining a balance, whether it is fluid, we get thirsty, we drink, same thing with hunger, all these other things. And then temperature is no different. So it starts with the skin feeling those receptors. They send that message up to the brain. It sends out this order of responses. Nervous system response, this is different. So after a while, I'm going to get into this a little bit more when we start to get into exercise. After a while, our nervous system will actually not be able to activate our muscles as effectively. So this is something that is worth noting. When you're exercising in cold weather, if you're having trouble or if you're not adequately warmed up, or if the weather's just extremely cold, or if you've been out there for a long period of time, your nervous system cannot get your muscles to function the way they would normally. So if I were to take someone and have them do a maximum bench press inside of a gym, and it's like 70 degrees inside the gym, and their max bench press is 200 pounds. Now we go outside, no warm up, just like we did in the gym, but the temperature is like 35 degrees. Their max is almost certainly going to be less. If I were to also record the speed of how fast they do it, it's also going to go down. So speed, strength, and those combinations overall power, those for their muscles all go down. What that means is you can't exercise with the same intensity. And then what that means is you can't generate as much heat. The higher intensity we work out, the more heat we generate, right? If we sprint, we heat up quicker than if we walk, you know? So that's something definitely to keep in mind, that if you're really at those extreme ends and you're feeling those effects, your body's not gonna be able to, counter the cold as well. And if you're trying to do a certain workout or anything with a standard to it that you're trying to hit, you're not going to be performing as well. And you see that in a lot of sports like football when they start in the summer and then they end in the cold winter. Places like, they have Green Bay up in Wisconsin, stuff like that, versus like Miami, very different areas. So you see those kinds of effects happening on certain people. And then I wrote breathing a little bit separately. So what I thought was interesting, because we can get things like frostbite, hypothermia, all these other things we've already kind of talked about. Breathing, a lot of people get concerned with, and we feel like we can't breathe very well in the cold. But the research was pretty definitive when I was looking it up, saying that if it's as cold as minus 19 degrees Fahrenheit, and you're breathing in your regular air, by the time it gets to the back of your nasal passage, which is about 2 inches, that minus 19 air is already about 60 degrees. So, and then by the time it gets down into your lungs, it's perfectly like warmed up again. So if you think about it, you've never really gotten a brain freeze from breathing cold air. At least I've never heard of that happening. So I thought that was very interesting that for some reason, when it comes to breathing, we're really well adapted and we can actually withstand pretty extreme temperatures, which is, it's good to know that we don't have to worry. Different in the cold though, different in the water. Remember, water is 4 times more effective and can really affect a lot more. But the only thing to keep in mind with breathing is that if our core temperature does drop too much, the function of trying to breathe starts to go away. So not that our airways have any issues, but we can't get the air in and out. Our diaphragm can't function as well. So even if your airways are perfectly fine, you still need to be able to pull the air in and out. So just keep that in mind. There's that other part of breathing. So the effects. The change in muscle effectiveness I just went over. Change in energy with exercise. This is a little bit different. So basically what happens is, and we're going to go into a little bit more in just a minute, but when you're exercising, obviously your muscles need energy. Where you get part of that energy is from fat, which we showed a slide ago, comes from the skin, or outside underneath the skin. But when we're in the cold, we change the amount of blood flow that we're sending there to try to keep our bodies warm. So even though you might be breaking down fat the same way, you're not able to actually get it over to the muscles. And then once they start to lose their energy, they're not going to be working as hard, which is going to, and this is where I go into this third point, snowball effect. So if your muscle doesn't have as much energy, like you're getting really tired, you can't work as hard, right? We've all experienced that. We all work out. When we get tired, we can't work as the same as we want to. So change in energy because of that blood flow to the fat changes how well the muscles work. They can't work as well. They're not going to generate as much heat, which is going to start to decrease the body temperature, which is going to tell the nervous system that it can't get the muscles to function as hard. And that's going to kind of lead to this spiral, which can kind of decrease over time more and more. So if you really start to feel the effects of fatigue when you're outside in extreme cold, or if you, for some reason, just suddenly, like you don't feel tired, you feel like you're mentally ready to go, but your muscles just aren't getting it done and something's going on, you can't pinpoint it, keep in mind you could be starting to fall into this spiral. We're going to go into it a little bit more, but there's so many factors. People are different. They might have adaptations to cold. They might have different body temperatures. Someone has more muscle versus fat. There could be more wind. There could be more layers on. There's so many different things. So it's really, there's no formula to know exactly at this point you're in the problem zone versus at this point. But just things to keep in mind and just really, pay attention and listen to your body when you're out in some harsh cold. Well, go back. Okay, so sorry, that picture was supposed to pop up. she's obviously warming up and she's well layered and stuff like that. So you want to make sure that you keep that in mind to help, prevent all of this. So what happens in cold environments continued. So this is where things get a little bit rough. And I wanted to go over how bad could it be, like what happens to our body. So hypothermia is going to be, for sure when your core body temperature is below 94 degrees Fahrenheit. So we're normally trying to be at 98.7, something like that, 98 degrees Fahrenheit. When we go below 94, now we're hypothermic for sure. What that means is that your brain has trouble regulating temperature. So I mentioned the brain and the nervous system can't activate muscles as well. This is a little bit different. This means that like when your brain says, okay, we're cold, start to slow the blood flow down to the skin, the brain's having trouble getting that done now. And I was explaining this to somebody before, and I was like, think about like an army base or whatever military base, and there's a lot of soldiers there, and they all know what to do. Let's say they're getting attacked and they all have to go to their battle stations, but for some reason, none of them have boots on anymore, and none of them have like clothes anymore or something like that. They're not going to move as fast, right? They're not going to be as functional without all their gear. So it's kind of like that. Like your body's trying to do the right thing, but it just can't quite get it done. And without going into too much detail with the science, the responses by the cells are slowed down. So your cell is a living thing, just like we are. Basically, once they start to cool down, they can't function as fast. Just like when we're super cold, we can't move as fast. So it's the same kind of idea within your cells, which means they have trouble kind of getting their jobs done. So that's at 94. Once we get below 85 degrees Fahrenheit, your brain actually loses the ability to control your temperature. So it went from having trouble to do it to now I can't do it anymore. That's when it's really bad. So recovery must be slowed. What that means is like if you're outside and something happens, maybe you get injured and you can't quite get back to your car or something like that, but you're outside for just too long, you can't just jump into a warm house and get hot chocolate and then be good. It actually, you have to do it slowly, otherwise you can really cause some permanent damage to your tissues. And then if it gets too low, the recovery must be done medically by a doctor or hospital or whatever. Interestingly enough, and I couldn't find any details on how physiologically this works, but in certain instances when during medical procedures, they will actually purposefully decrease the core body temperature to as low as like 65 degrees. How they do that, I'm not sure. I don't think it's as important as how they bring it back, but for somehow medically, they have the technology and procedures and stuff like that to purposefully cool you down to a core temperature of 65 degrees, which is super cold. You can almost go into a coma at that point, and they can bring you back. So if you do get super, super hypothermic, there is a chance of them bringing you back, and you don't have to worry too much. Frostbites is a little bit different. So what this is basically the decreased blood flow to the skin, which combined with the cold already causes accelerated tissue death. And so this is a little bit like when I said the cell responses are slowed because they're feeling cold. This is kind of like the extreme end of that on your skin and your surface. So the intracellular fluid, basically like fluid inside of our cells, you can think of it like a cell's blood, if you will, literally starts to freeze. And that means that it can't get nutrients anywhere, it can't get oxygen anywhere, and it's just kind of stuck. So that's what happens in frostbite, and we obviously know that that's bad, so we don't want to do that. So exercising in the cold. We've already talked about this a little bit, so there's multiple variables, and like I mentioned. So up top, I have all the different kind of applications why people want to research this. Polar plunges, those kinds of like weird tournaments and stuff. Ski and snowboarding, the industry, which is a whole different thing. Then of course, Winter Olympics, the competitive sport. Military, not only ours, but anywhere else. And then just people living in the north and in the cold. All of these applications, they have some sort of funding fuel to try to figure out ways to adapt in the cold, understand it, all those questions, they want them answered, that kind of thing. But all these variables underneath, weather, like we mentioned, specifically wind, water, humidity, those are all factors. The sun, your own clothing, your body composition, I mentioned, any kind of adaptation. And then specifically for exercise, the type. So jogging, walking, like I mentioned, sprinting, heavy lifting, those are all entirely different. So one of those examples that they seem to know pretty well, endurance exercise, long distance, they usually start out okay, as long as you've gotten a good warm up or you're well dressed, that kind of thing. And then you'll do well, pretty well in the beginning. Preparation is something important. So this is what to take home from this. So clothing in particular, what you want to do when you're starting an endurance exercise, obviously you want to warm up a little more thoroughly than you would in the summertime because you're not used to the cold. You're used to, we like to stay inside, right? Um, so that kind of goes without saying, but clothing wise, when you're about to start your full on exercise, you want to be just a little bit cold. The reason why is because you don't want to start comfortable, because as soon as you really get going, you're going to heat up and then you're going to sweat, and that's going to cool you way down. And that water is going to cool you down 4 times faster than that exercise is going to be able to heat you up. So keep that in mind. So they say to start a little bit cold. And also part of preparation, whenever, wherever you finish your exercise, have something there to put back on, another layer to warm yourself back up. Even if you feel super warm right off the bat, you'll change really quick, and don't wait to be cold and then try to react. Put it on right away. Keep that warm feeling wrapped up in you, and it'll be really good. And then the other things I mentioned, energy over time and that snowball effect. So you want to make sure that you prevent that as you lose energy just because of your endurance exercise, your muscles won't work as hard. They won't be able to heat you up as much, especially if you were sweating before. You're going to start to get colder, can't activate them as much, and it's just this vicious cycle over and over and over. So you just want to be aware of that. Um, Exercise benefits. So we're trying to exercise for a reason, right? Either we're training for a sport, which we mentioned all about performance, or we want to like lose weight or something like that. It's the holiday season and all these kinds of things. So energy burning slash usage. Basically what I mentioned is that you're trying to burn all this fat, but you can't get it to your muscles as well. And once your muscles don't get the energy that they need, they can't perform as well. So what you might want to do, and take this properly, is consume a little bit of food or something with some carbs in it before you exercise. Not super close that it's going to bother your stomach, and not a lot, but a little bit so that you have some additional energy ready to go and you're not going to hit this wall. And that's that snowball prevention, food. So you want to make sure that you're keeping mindful of that. And then you want to stay consistent, because if you're burning this fat but it's not going anywhere and it sits there, and then the next day, you're not getting as good of a fat burning over time as you would want to. So definitely something to keep in mind. You want to keep your consistency up, because it's going to be little bits over time. It's just not going to be as much progress as we would like. Improved warm-up benefits, question mark, question mark. So we're warming up more thoroughly. Usually we start out, if we can, start out inside, warm up, get your body going, and then go outside. But because we're warming up more, yeah, that up over time, it's kind of like more exercise over the course of a month. So they don't know the details, but there could be some additional calorie burning there, which is kind of a cool little benefit. So we went over all these like bad things, but don't be afraid, because there's a few instances here where people have done extreme instances in the extreme events, accomplishments, those kinds of things in the cold. So Mount Everest, obviously that's a guy climbing Mount Everest. It's the highest peak on our planet above sea level, at about 29,000 and change above sea level. And the average temperature there throughout the year is minus 15 degrees Fahrenheit. And you can see a guy there climbing it. And because of the oxygen amount, they actually usually climb it when it's colder, because when it's colder, there's a higher pressure. And with a higher pressure, it's easier to get that oxygen inside their lungs. So they will not be able to breathe during those warmer, relatively more comfortable months. So they actually go up there when it's super, super cold. Next, this is a town in Russia. It's the coldest town on our planet. It's called Oymyakon, I think. That's how you pronounce it. I did a presentation about this in grad school, and I had no idea this place existed, but it had the record low temperature. I think that's actually incorrect. I think it's minus 96 degrees Fahrenheit, which is almost the temperature of dry ice. It's like 10 degrees off. So that's literally where carbon dioxide in the air will start to form dry ice. And I mean, literally, like the entire town is completely covered in ice all year long. I think the record high temperature is like 34 degrees Fahrenheit ever. So that's a town in Russia, and it's in like a super remote area in Siberia. It's crazy, and it's a town of like 30 people maybe. I don't know how they got there, why they're there, what it's like to live there. I don't know. Not many people want to go out there to report about it for obvious reasons, but it exists and they're able to live. So pretty impressive. Good on them. I'll pass. Okay, so Antarctica. Of course, we know about this. Average winter temperature is minus 56 degrees Fahrenheit. We're now at the poles. We don't have sun all the time. So as we know, it gets colder at night. Imagine nighttime to nighttime to nighttime for like a couple months. It gets super, super cold. But there's been a lot of different exercise events out there. I think people have done marathons out there. Obviously, they're doing research. You can do a lot of like, what's outer space research or whatever with like the constellations and that kind of thing. You can stand there for selfies like this guy is. You know, you can do. We've been able to do a whole bunch of different stuff up there, but their average winter temperature is minus 56 degrees Fahrenheit. So when it's 30 degrees outside, 20 degrees outside, just plan accordingly. Really take the time, take the couple extra minutes to plan your warm up and plan your clothing situation. So before, during, and after. You know, go outside, see what kind of clothing you're going to need to prevent yourself from sweating. Be just a little bit cold beforehand. Warm up beforehand. Have something ready right after. Whether you're going for a lap around your block or you're driving out to a park to do some pull-ups or something. Any one of those things, just keep that in mind. But if it's 20 degrees outside and it's super cold and it's crazy, you can do it. You'll be all right. I believe in you, and I know that if you just take the time to prepare, you'll be good because all these folks are able to do it. Once again, I'll pass on any of these, but also go out and get my run in over the weekend. So that being said, we have a couple minutes left before the Zoom meeting cuts us off. Are there any other questions about any of these? None at all?
No, I think that was great.
Awesome. I'm glad.
Just be more prepared before you go outside is my takeaway from it, which
Yeah.
is fair.
Yeah, no, definitely. That's exactly what you want to do. It's all about preparation because, you know, you're not going to get up and in the spur of the moment go to Antarctica, right? Certainly wouldn't recommend it, but people can
No, but
prepare and do it and make it happen. So
yeah,
yeah, and then like anything
yeah,
else, once you do it a couple times, you get into the hang of it and you have it all dialed in.
yeah, no, that makes sense. I'm really guilty of bundling up too much, I think. When I go
Yeah,
out, what you said about make sure you're a little bit cold
yeah.
so
I
that
don't
you're
mean to
not
cut you off, but the
suffocating.
Zoom is about to shut us off. So we can
Yeah, no, I know.
in a
I
minute.
know. Thank you, Sean. That was really
Thanks,
helpful.
Sean.
Awesome. Thank you guys. I'll jump back on in just a minute.